Welcome back to The Deep Dive. Today we are strapping ourselves in for a deep exploration of, well, arguably the most ambitious, complex, and politically charged flying machine ever built.
NASA's Space Shuttle system.
Exactly.
And officially, it was known as the Space Transportation System, or STS. And to really appreciate what we're talking about here, you have to understand, it wasn't just a rocket.
No, it was a promise.
It was a promise. A partially reusable, low-Earth orbital spacecraft system that spanned 3 decades. It operated from its first flight in 1981 all the way until its retirement in 2011.
And that 30-year run. I mean, the metrics are incredible. 135 total missions flown.
Resulting in 133 successful launches. Okay. And when you add it all up, the total fleet time for all 5 orbiters was an astounding 1,323 days in space.
But those numbers, they only really hint at the monumental scope of what the shuttle was supposed to do.
Exactly. The program's primary roles evolved so dramatically, really reflecting the changing needs of science and geopolitics. It was first conceived as this sort of routine space truck.
Right, to lower launch costs.
To lower launch costs.
Yeah.
But it ultimately became the primary delivery system for the most critical payloads of its time.
And we're talking about massive military reconnaissance satellites, groundbreaking instruments like the Hubble Space Telescope.
And deploying these incredible long-range interplanetary probes like Galileo to Jupiter and Magellan to Venus.
And then later in its life, it was the irreplaceable construction crane for the International Space Station.
Which was the largest engineering collaboration in space history. And, that period was really defined by the diplomatic and technical cooperation that came right before it with the Shuttle Mir program.
So to put this all into historical context, the entire STS system was basically the sole survivor of a much grander plan.
It was. It was the only item that actually got funded out of Vice President Spiro Agnew's comprehensive 1969 proposal for a fully reusable spacecraft.
They wanted this routine, almost airplane-like path to orbit, and the shuttle was NASA's attempt to deliver on that massive ambition.
And you can see that ambition in its very structure. When you saw that enormous vehicle on the launch pad, you weren't looking at a single machine.
No, you were looking at 3 fundamentally different components, all working together for a vertical launch.
Let's break those down because their design really dictated the operational challenges and the cost.
Okay, first up, the central element.
That would be the orbiter vehicle, or OV. The sophisticated winged craft with the crew, the payload, and those 3 clustered, reusable RS-25 main engines.
Then flanking the orbiter, you have the 2 enormous white, recoverable, solid rocket boosters.
The SRBs, the initial blistering thrust.
And wrapping it all together was that massive orange expendable external tank. The ET, it was the fuel canister, feeding the orbiter's main engines all the way up.
It was famously dubbed a stage-and-a-half system.
Why that name?
Because the orbiter's engines fired from the moment of ignition all the way to orbit, using fuel first from the boosters and then the external tank. And this mixed architecture, part rocket, part airplane, part expendable, part recoverable, that's where all the engineering compromises lived.
It's what made it unique.
And frankly, what made it so labor-intensive and costly to operate.
Okay, let's unpack that unusual architecture. And let's start with the raw, terrifying power that got that stack moving. That all came from the solid rocket boosters.
And what's fascinating here is the sheer brute force they generated. While the orbiter's RS-25 engines were these precision instruments, the 2 SRBs were just pure muscle.
They provided a jaw-dropping 71.4% of the total thrust at liftoff.
Just an immense figure.
And their size was commensurate with that power. They were, in fact, the largest solid propellant motors ever flown.
45 meters tall, nearly 150 feet. They dictated the entire rhythm of the first 2 minutes of flight.
And that's all they had, just 2 minutes.
That's it. They burned with incredible intensity for just 124 seconds, and then they were jettisoned. They separated at about T plus 123 seconds at an altitude of around 46 kilometers. But the key here, the complexity, was that the SRBs were the first fully reusable, large-scale components in the stack.
And their recovery process often gets glossed over when we talk about reusability. It was anything but simple.
Oh, it was an incredible logistical operation. Once they separated, they deployed these massive drogue and main parachutes, eventually splashing down vertically in the Atlantic.
And then the ships had to go get them.
Right. The specialized recovery ships, the MV Freedom Star and MV Liberty Star, had to locate them, winch them out of the water, and tow them all the way back to Cape Canaveral. A full-day operation.
And once they were back on shore,
the massive casings were cleaned, disassembled, and then shipped all the way across the country to Thiokol in Utah for meticulous inspection, refurbishment, and reloading with new propellant.
That turnaround time alone was a massive operational overhead.
Absolutely. The pursuit of reusability, however, was fundamentally challenged by a tragic flaw in that original design.
Which leads us inevitably to the Challenger disaster in 1986.
Right. That loss, STS-51L, it stemmed from the failure of a tiny component, the O-ring seals. See, the SRBs were built in segments, 4 large sections stacked and joined together.
And each joint had 2 rubber O-rings to contain the immense heat and pressure.
And the tragic consequence of the low temperatures on that specific launch day.
It was so cold.
The cold caused the rubber O-ring to stiffen, so it couldn't seat correctly and seal the joint. This allowed high-temperature gas to erode the seal, breach the secondary O-ring, and escape. Basically like a blowtorch.
Hitting the external tank and the orbiter's wing.
And following the disaster, the SRBs underwent mandatory extensive redesigns to introduce a constant leak-proof seal no matter what the temperature was.
So the SRBs were the reusable, powerful workhorses. Now let's talk about that massive orange backbone in the middle, the external tank.
The ET. This was the part that never came back.
It was the largest single component of the whole stack.
Right, structurally integrated to carry the thrust loads from everything. Its only purpose was to hold all that cryogenic propellant, liquid hydrogen and liquid oxygen, for the orbiter's main engines.
And its visual evolution is a great marker of NASA's constant struggle to shave every single ounce of weight off the system.
Absolutely. The first 2 missions, STS-1 and 2, they had white tanks.
Why white?
It was a thick, white, fire-retardant latex paint applied over the foam insulation. But that seemingly benign layer of paint added 270 kilograms, almost 600 pounds, to the tank's dry weight.
Which, in the brutal economics of getting to orbit, is payload capacity you're just giving up?
Precisely. The engineers quickly realized the paint offered negligible protection, so they just stopped painting it.
And that's how we got the iconic rust orange color of the foam that we all remember.
Exactly, starting with STS-3. But the evolution didn't stop there. As the shuttle matured, especially for the big ISS missions, they needed to lift heavier components.
So they had to find more weight savings.
This led to 2 major upgrades. First, the lightweight tank, or LWT, which saved a significant 4,700 kilograms by thinning some aluminum panels.
Over 10,000 pounds.
A huge saving. And then came the ultimate version, for the really heavy ISS assembly lifts.
The super lightweight tank.
The SLWT, introduced in 1998. And the genius here was material science. They swapped out the old aluminum alloys for a much stronger but lighter aluminum lithium alloy.
And that saved how much?
Another 3,500 kilograms.
Yeah.
So when you needed to boost massive modules like Unity or Tranquility to the ISS, those cumulative savings, nearly 8 metric tons in total, weren't just improvements. They were what made the later program possible.
But no matter how light they made it, the ET was always destined for destruction.
It was the one truly expendable piece. It would separate just before the orbiter reached full orbital velocity, tumble, and then break up harmlessly during re-entry over the Indian or Pacific Ocean.
Okay, now we transition to the true technical tour de force. The orbiter vehicle itself. This machine had to pull off this spectacular duality.
It had to survive the extreme forces of ascent like a rocket, and then hours or days later, function as a delicate, unpowered hypersonic glider.
That synthesis of roles is where the complexity just skyrockets.
It does. Let's start with the heart of its propulsion. The 3 RS-25 main engines, the SSMEs, nestled in that triangle pattern on the back.
And these weren't just big engines. They were incredibly advanced, designed for reuse and extreme performance.
They were the first fully reusable, high-performance engines ever built. And the key technical detail is that they were staged combustion cryogenic engines.
Okay, break that down for us. What is staged combustion?
Oh, it's a highly complex process where propellant is partially burned in a pre-burner, and that gas is used to spin the high-speed turbopumps that push fuel into the main combustion chamber.
And why go through all that complexity?
Because it allowed the RS-25s to achieve unprecedented efficiency by operating at a chamber pressure far, far higher than any previous liquid-fueled rocket. That immense pressure translated directly into the thrust they needed.
And this complexity paid off in versatility. They weren't just on or off.
No, they were throttleable. Absolutely crucial. They could gimbal, meaning swivel, to steer the vehicle.
Yeah.
And they could be throttled down to 65% power to survive the peak atmospheric stresses.
That point of peak stress, that's max Q, right?
That's right. Max Q, maximum dynamic pressure. It happens about a minute into the flight, And it's when the aerodynamic forces trying to rip the vehicle apart are at their highest.
So throttling down was essential to ride that out.
To feather the sails, so to speak, without sacrificing the vehicle's structural integrity.
Okay, so once the RS-25s cut off and the ET was jettisoned, the orbiter still needed a final boost and maneuverability in space. That was the job of the OMS.
The orbital maneuvering system.
Right.
2 secondary engines in those big pods on the tail, and they used hypergolic fuel.
A critical distinction.
It is. Hypergolic fuel is basically 2 chemicals that instantly ignite on contact. No complex ignition sequence needed.
And in space, reliability is everything.
Exactly. The OMS engines offered reliable, repeatable, fast-acting thrust. They were used for the orbit insertion burn, all the orbital changes, rendezvous, and most critically, the deorbit burn at the end of the mission.
Let's talk about the people inside this technical marvel. The crew roles were highly specialized.
You had the core crew, the commander and pilot, responsible for flying the vehicle. Then you had mission specialists who handled payloads, experiments, and did the spacewalks.
And then you also had payload specialists who were often unique to a mission.
Yes, often scientists or experts from, say, the European Space Agency flying with a big payload like the Space Lab module.
And the safety systems for the crew saw a major, tragic evolution over the program's history.
The evolution of the pressure suits told a grim story. Initially, on the first 4 test flights, the crew wore full pressure suits. But then, from STS-5 until Challenger, they wore only simple Nomex flight suits.
Reflecting that original promise that the shuttle was as safe as a commercial airliner.
An approach that, tragically, proved unsustainable. Post-Challenger, they introduced the Launch Entry Suit, or LES, a partial pressure suit.
Yeah.
And then that was superseded by the full-pressure Advanced Crew Escape Suit, the ACS suit.
The pumpkin suit.
The orange pumpkin suit, right. Designed to protect the crew during a high-altitude emergency bailout.
It's also worth noting that the very first orbiter, Columbia, actually had ejection seats.
It did, for the first 4 flights.
Yeah.
But they were deemed impractical. They only worked for 2 crew members, not the typical 5 to 7 person crews. So they were disabled after STS-4 and removed entirely after STS-9.
A clear sign that NASA was banking heavily on the safety of the vehicle itself.
They were.
Okay, moving to the nerve center, the cockpit and the computer system. The shuttle was entirely fly-by-wire.
Completely. It relied on 5 general-purpose computers, or GPCs. The system was designed around quadruple redundancy for the primary flight software called PASS.
So 4 computers ran the exact same program, constantly cross-checking each other for errors.
Precisely. If one computer had an error, the other 3 would outvote it. But this system was vulnerable to a common mode failure.
If the software itself had a bug,
All 4 computers would fail at the same time. And that is why the 5th computer existed, running the backup flight system, or BFS.
developed by a completely different contractor.
Different contractor, different programming methodology. If the crew suspected an error in PASS, they could manually switch control over to the BFS. It was the ultimate safety net.
And this reliance on specialized software even led to a really niche, almost comical glitch late in the program.
It's a great story. In 2007, engineers discovered the flight software needed a patch because the original code hadn't accounted for flights crossing the year-end boundary.
The Y2K bug, but for the shuttle.
Basically, the system would crash if it went from December 31st to January 1st in flight, forcing a complete reboot. Not something you want to do while docking with the ISS.
That detail perfectly illustrates the sheer depth of engineering. Now, let's pivot to the greatest engineering challenge of all. Surviving re-entry, the thermal protection system, the TPS.
The TPS was the orbiter's life support during that fiery return. Unlike old capsules that used ablative shields that burned away, the shuttle needed a multi-use system. Its job was to keep the aluminum airframe below 180 degrees Celsius,
About 350 Fahrenheit.
despite external plasma temperatures reaching a blistering 1600 Celsius or 3000 Fahrenheit.
And the heat wasn't uniform across the vehicle, which meant the TPS was a patchwork of different materials.
This is a crucial detail. The absolute hottest points, the nose cone and the wing leading edges, were protected by reinforced carbon-carbon, or RCC.
And what protected the rest of the underside? The black tiles.
The belly was covered in high-temperature reusable surface insulation, HRSI, the famous black tiles. They were made of borosilicate, glass-coated silica fibers, mostly empty space, making them incredibly light and great at dissipating heat.
And then you had the water tiles for the less critical areas.
Exactly. Low-temperature reusable surface insulation, or LRSI, for the upper fuselage. And finally, the coolest areas, like the payload bay doors, were covered by flexible insulation blankets. It was a massive, delicate jigsaw puzzle.
And once again, a failure of the TPS led to the ultimate tragedy, the loss of Columbia in 2003.
Right. The Columbia disaster occurred because of damage sustained during launch. A large piece of insulating foam fell from the external tank and struck the RCC leading edge of the left wing,
And that breach allowed superheated air to penetrate the wing during re-entry.
causing catastrophic failure. And this tragedy fundamentally changed orbital operations for the rest of the program.
It ushered in the era of mandatory on-orbit inspection.
It did. The surviving orbiters were retrofitted with sensor suites and a highly specialized inspection boom, an extension for the Canadarm.
So they could scan the vehicle for damage after launch.
Immediately after achieving orbit, they would scan the leading edges and the nose cone. If damage was found, they would attempt an on-orbit repair or plan a rescue mission.
That requirement for inspection added yet another layer of immense complexity and cost to every single subsequent mission.
It shifted the entire risk management structure. Before Columbia, they assumed the orbiter would launch undamaged. After, they had to assume damage was possible and be prepared to deal with it.
Moving from the intense dynamics of re-entry to the operational phase in orbit, the orbiter transformed into an incredibly capable science platform and delivery truck.
And its capability started with its physical size. The payload bay was breathtaking, 18 meters long, 4.6 meters wide. Revolutionary for launching things like large satellites or entire space station sections.
But those massive payload bay doors served a vital secondary function.
They were massive radiators. Once in space, the crew had to open those doors to expose the radiator panels inside. Without the ability to radiate excess heat into space, the orbiter would quickly overheat.
And managing all that cargo was the legendary Canadarm.
An amazing piece of robotics, controlled by astronauts using hand controllers while looking through the aft flight deck windows. It had 6 degrees of freedom, allowing for deployment, retrieval, and manipulating massive ISS components.
It had to be incredibly strong.
It was, initially rated to handle payloads up to 29,000 kilograms. But as it evolved, it was capable of maneuvering objects weighing up to 270,000 kilograms. It was also critical for EVAs, acting as a mobile work platform for astronauts.
And the shuttle also served as a dedicated lab with the European Space Lab module.
Spacelab flew on 28 missions. It was a pressurized lab in the payload bay, connected to the crew cabin by a tunnel. This allowed non-astronaut scientists to conduct research in microgravity in a shirt-sleeve environment.
It really demonstrated the orbiter's unique role as a short-term, in-orbit science center.
It did, and as the ISS grew, they even developed a way to draw power from the station while docked.
The Station-to-Shuttle Power Transfer System, or SSPTS.
Right. It let the orbiter convert and use power from the ISS solar arrays, which extended the dock time by several days, essential for completing complex construction tasks.
Once the orbital work was done, the orbiter began its final act, re-entry and the unpowered glide landing, a sequence that started at Mach 25 and was incredibly unforgiving.
It all started 4 hours out, closing the payload bay doors. Then the crew oriented the orbiter upside down and tail first for the deorbit burn.
A short 2 to 4 minute OMS burn, just enough to slow it down to drop into the atmosphere.
Then they reoriented, nose forward, at a steep 40-degree angle of attack for re-entry.
That high angle was deliberate, right? To present the heat-shielded belly to the atmosphere.
Exactly. Maximum drag, maximum protection. Re-entry started around 120 kilometers altitude, traveling at hypersonic speeds.
So since it was an unpowered glider, how did the flight computers make sure it hit a tiny runway thousands of miles away?
This is maybe the most impressive part. The trajectory was controlled dynamically using aerodynamics alone. The primary method for steering was altering the bank angle.
Which required those famous roll reversals.
Exactly. The orbiter would roll sharply to one side, increasing drag and correcting its course, then rapidly reverse the roll to the other side to stay on the glide path. It was like constantly hitting the air brakes and steering purely with friction and lift.
It sounds utterly terrifying. A heavy, unpowered vehicle with the aerodynamic qualities of a brick.
Its glide ratio was only about 4.9 to 1 once it was subsonic. A commercial airliner is more like 15 or 20 to 1. It fell fast.
And the crew only took manual control at the very end.
Right, well into the subsonic regime. The landing gear was deployed a mere 10 seconds before touchdown.
And the touchdown was fast.
Very fast, up to 340 miles per hour depending on the weight. Immediately after touchdown, they deployed a drag chute to slow down, with wheel braking only starting at lower speeds. A high-stakes precision maneuver.
And landing meant the mission was over, but the cycle of expense and complexity was just beginning again. The support infrastructure was immense.
Staggering. The goal was always to land at Kennedy Space Center. But 54 landings happened at the alternate site, Edwards Air Force Base in California.
And if they landed there, they needed a ride home.
That's where the shuttle carrier aircraft, the SCA, a modified Boeing 747, came in. It would ferry the orbiter back to Florida.
Then the orbiter was taken directly to the Orbiter Processing Facility, the OPF, which was the true cost sink of the whole reusability idea.
This was the heart of the refurbishment cycle, and it was painstaking. It involved draining consumables, removing payloads, and then the exhaustive manual inspection and repair of every single one of the thousands of heat shield tiles.
And the RS-25 engines themselves were another layer of complexity.
They were actually removed entirely from the orbiter and serviced separately. They required teardown, inspection of the high-stress turbopumps, and extensive maintenance before they were certified for the next flight. This complex cycle is why the shuttle never achieved the rapid turnaround its designers dreamed of.
Let's pull back and look at the big picture. The shuttle tells the story of unmatched technological triumph built on a very costly, flawed economic premise.
It was sold on the promise that reusability would drive down the cost per launch through an extremely high flight rate. They were projecting 24 flights per year.
These expectations were never remotely met.
Not even close. The highest flight rate ever achieved was 9 in 1985 and 1997. And the costs ballooned. When you factor in the entire program budget, the actual cost was a staggering $1.642 billion per launch.
So why did the economics fail so completely?
Because the reusability was only partial, and the recoverable parts, the orbiter and the SRBs, were incredibly expensive to refurbish. It required thousands of technicians, weeks of manual labor, and highly specialized facilities. It was reuse, yes, but it was high-cost reuse.
And beyond the finances, the shuttle's tenure was tragically marked by devastating safety risks, which led to intense criticism of NASA's safety culture.
The engineering risk of catastrophic loss was far higher than publicly advertised. Retrospective analyses suggested the risk might have been as high as 1 in 9 for some early missions.
Instead of the 1 in 100,000 some managers were claiming.
And both the Rogers Commission after Challenger and the Columbia Accident Investigation Board were damning in their conclusions.
And the recurring theme in those criticisms.
NASA management was criticized for institutional failure, for ignoring engineering warnings and allowing schedule pressure to increase risk. They suffered from what's called normalization of deviance, where they learned to live with known flaws until tragedy struck.
The retirement of the fleet was announced in 2004, tied to finishing the ISS.
The program officially concluded after STS-135 in July 2011, leaving the U.S. without its own crew launch capability for almost a decade.
Now, the operational orbiters Discovery, Atlantis, Endeavour are iconic museum pieces.
They are. But even that required a massive demilitarization and purging process to make them safe for public display. All the toxic propellants had to be neutralized and removed.
And this brings us to the truly enduring and maybe ironic legacy of the shuttle. Its hardware is still the backbone of American spaceflight today.
It's the ultimate recycling story. The Space Launch System, or SLS, the vehicle for the Artemis program, is essentially built around refurbished shuttle hardware.
So we're still using RS-25 main engines.
Up to Artemis IV, and the massive SRB steel casings up to Artemis III.
So we retired the shuttle because it was too expensive to refurbish, yet we are refurbishing its most expensive parts to power the next generation of exploration.
It's the core paradox. The Artemis I mission utilized components that had previously flown on 83 of the 135 shuttle missions. Even the Orion spacecraft uses refurbished OMS engines from the 80s. The shuttle-proof hardware can be reused, but the SLS demonstrates that the expensive, labor-intensive cycle of refurbishment is still the default for NASA's biggest projects.
So in summary, the shuttle was this monumental technical success that let us build the ISS and launch Hubble, but it was built on an economically unsustainable premise of reusability.
It proved reusability was possible, but not that it was affordable. It was a necessary stepping stone. It taught us that true low-cost access to space wouldn't come from just bringing hardware back, but from radically streamlining what you do with it after it lands.
And yet today, we are still relying on those very same engines and casings for the Artemis missions, continuing that costly, complex cycle.
And this raises an important question, one that really defines the current space race. When will the cost equation truly flip? When will we finally move beyond the limitations of the shuttle's partially reusable, high-maintenance design and achieve the genuinely low-cost, routine access to space that was first envisioned over 50 years ago? Is the future of spaceflight defined by that expensive refurbishment cycle, or by the rapidly reusable, low-maintenance vehicles being pursued by commercial partners today?
That is a profound thought for you to mull over. It's a legacy that continues to define our challenges in spaceflight today. Thank you for joining us for this deep dive into the incredible architecture and complex, costly legacy of the Space Shuttle system.
My pleasure.
We'll see you next time for the next deep dive.